A very good day to everyone. So now our team group 10 will be presenting about the proposal for fire suppression system design. Before that, let me introduce myself. My name is Rexirona Robert and I will present as the fire and rescue officer. This schematic diagram was provided by the building developer or owner. It shows the water flow from the ground tank through the pump along the ground flow pipe up the main riser and finally to the four sprinkle nozzle on the top floor. From the fire safety view, the main concern is whether the system can deliver enough water to be the highest flow during an emergency. Now I will explain the main fire safety problem of the system. The main problem in the system is not only about moving water through pipes. The main issue is whether the sprinkler can work properly during a real fire. On the technical side, the top floor nozzle are located 12 meters above the tank base, while the tank only provides 3 meters of static head. This means gravity alone is not enough to supply water to the top floor with the required velocity. From the fire and rescue perspective, this is a serious concern. If the nozzle spray is weak, the fire may not be controlled early. This can cause the fire to spread faster, produce more smoke, and increase the danger to both occupant and firefighter. So, for the diagnosis finding, we will calculate the pump head first by using the Bernoulli equation. Based on all this information given, we can substitute it into the Bernoulli equation and found out that our H pump is equal to 15.77 meter. So for the next is for Reynolds number calculation. By substituting all this value given, we can see that the Reynolds number is 180,573.1. And after that, we can substitute the value of Reynolds number into the Colebrook-White equation to find the friction factor and doing it for three times for the iteration. We can also double confirm the friction factor value from this Moody chart, and based on after we get the value which is 0.016, we can confirm that the value is almost similar to the friction factor that we calculate in the iteration. So for the head loss calculation, we can divide it into two parts, which is major and minor losses. So for the major losses, after substituting all the value, we can see that the value is 1.1009, and for the minor losses is 2.4057. By adding both of these value, we can see our head loss is equal to 3.5066 meter. So now for the L1 resistant force, we can see this is the control volume diagram for the 90 elbow, and here is the linear momentum equation for both x-axis and y-axis. So this is the calculation for the x-axis. We can use the Bernoulli equation to find the pressure inlet, and after that we can use the value pressure inlet to find resistant force at x-axis, which is at 99.77 Newton. So this is for the y-axis calculation. We also use the same method by using the Bernoulli equation to find the pressure outlet. And after that, we substitute the value inside the linear momentum for y-axis and find the resultant force for y-axis is at 4.69. So after getting both of the value for the force at x and y axis, we can calculate the resultant force, and the final answer is 1261.84 Newton.
So here's our proposed solution. First, the pipe network. We select a uniform DN80 pipe. It was chosen because of it safely limits the water velocity to 2 meter per second, safely below the code limit for pressurized fire lines, preventing internal erosion and excessive flow noise during peak demand. This is our final pipe network design. Along this network, we installed 12 fittings in total. These are 4 flange 90-degree elbows, 3 fully open gate valve for system isolation at the tank outlet, ground floor and top floor, 1 swing check valve at pump discharge to prevent backflow, and 4 branch T-junctions on the top floor distribution pipe. And these fittings contribute to a total minor head loss of 2.4 meters. Next, to address decertifying engineer, our momentum analysis of the 90-degree elbow at the base of the main riser shows a diagonal resultant force of 1,261.84 newtons, To guarantee the structural safety, we mandate a heavy duty steel anchor bracket or a concrete truss block that must be fastened directly to the structural wall to prevent joint separation under high pressure. So here is our pipe redesign. As shown earlier, the FP200 pump is undersized. To help correct this system mismatch, we upsized the main riser from DN80 to DN120 at 120 internal diameter. The pipe velocity drops to 0.889 meter per second, well within the code limit. Here is our revised system curve. This change flattens the curve and it drops the required pump head from 15.77 meters down to 12.89 meters. And this drastically reduces the physical strain on the pump, but still not enough as the operating point does not intersect the pump curve, as seen on this chart. Therefore, with the new diameter DN 120, the pump still cannot reach the required head needed. So, to give closing recommendations, we formally recommend this panel that the building adopts a design DN80 pipe layout paired with an upgraded DN120 main riser to reduce friction and lower long term energy costs. And the main riser elbow must be secured with a structural truss block. And most importantly, the specified FP200 pump must be rejected and replaced with a higher capacity pump of at least 12 liters per second rating. This is a critical life saving measure as it ensures future occupants have a smoke free evacuation path and it gives the fire and rescue department the immediate suppression they need to operate safely inside. For the developers, doing this correctly upfront prevents catastrophic property loss. It is safe, code compliant, and cost appropriate. Thank you for your time.